Okay, good morning everyone. Today we're going to talk about graphical syntaxes for domain-specific languages. And I will start by saying a few words about the importance of graphical modeling in software engineering and in model-driven engineering. We're going to talk a little bit about how to design effective graphical syntaxes. That's the theoretical part of this lecture. So what are good principles to follow in order to define a good graphical syntax. And then we'll get to the tooling part. So we'll talk about a framework that sits on top of EMF that we talked about yesterday. This new framework is called GMF. It stands for Eclipse Graphical Modeling Framework. And we're going to see what it involves, the extra facilities it involves, the kind of output you should expect from it, and also some of its limitations. And we're going to talk very briefly also about some of the competing frameworks to GMF. We're also going to talk about a tool that builds on top of GMF. So we have EMF, we have GMF, and then on top of that we have yet another tool called Eugenia. And the purpose of that tool is to simplify the development of common case GMF editors. And we're going to talk about how it does it by annotating equal meta models, and then how we can fine-tune the results and kind of get very close to the end result that we wish using policing transformations. But first things first, let's go into the theory part first. So I think it's clear that diagrams have a very important role to play in software engineering, especially when interacting with non-technical people. And software is usually just one part of the picture in most systems. There are business people involved. There are other types of engineers, electrical engineers, mechanical engineers involved. And we need to somehow communicate across these boundaries. So this is where diagrams play a very important role because they're quite intuitive to understand by people who are not familiar with the intimate details of what we're representing, and who would be lost if we were just to show them Java or any other kind of text-based programming or modeling language. So this example here, you don't need to understand much about what's going on to figure out that, well, if you get asked if you can move from any state to any other state, to quickly answer that actually here seems to be a problem. That wouldn't be so easy to do for someone who is not familiar with programming languages, for example, if we just showed them that switch statement. The reason why diagrams are so useful is because they actually make use of the power of our visual system. So visual representations, when we see a diagram, the visual system of our brain kicks in, which is highly parallel in nature. And that's why we can see a picture and we can immediately kind of get a feeling about what's happening there. Now, on the other hand, textual representations are processed serially by the auditory system, the same system in our brain we use to hear. And this is a much slower system. So we can extract a lot more information in one go from a diagram with little effort, because our brain is wired up like that. But it takes a lot more effort to actually go through text, because we go through it in a serial way, in a line-by-line way. Of course, both systems have their uses. Text is better, as we will see, for kind of concentrating and when we actually need to focus. But diagrams are quite good to get that kind of high-level overview of what's going on. Okay, so we're going to talk a little bit about how to design graphical syntaxes, and we should start with the big picture here. So what we're trying to do when we're visualizing, when we're producing a diagram, is we're trying to take an intended message from the head of a person over to the head of another person, right? And everything in between are just tools that we use to do that. So in this setting, the original method, the original idea lives in the head of the diagram creator, who needs to encode it in the form of a diagram. And then that diagram is decoded by the diagram user in order to understand and to replicate in their brain what the diagram creator intended. So the diagram, in this case, is just the signal, the medium through which this communication happens. So how does decoding happen? We have two steps. The first one is called perceptual processing, and this is where we kind of form the big picture of what we are seeing. This is highly parallel and very fast. And then we need to start focusing on individual subparts of the diagram. And this is where cognitive processing happens. And this is where we develop this deep understanding of what's going on, right? Where we start to reconstruct this model with more details in our head. And a good graphical syntax should try to minimize this part of the effort, which is hard and which is slow, and maximize the information we can extract in this first step. And we'll talk about how to do this, how to achieve this. There are certain principles. So there are 9 core principles that have been identified for designing effective graphical syntaxes that maximizes this bit and minimizes this bit, and we'll go through a few of them. So the first principle is called semiotic clarity. And this means that there should be, and under this principle, we should be trying to have a one-to-one correspondence between symbols and the concepts that they refer to. We could have a diagram where everything is a box, right? So like in the case of these flowcharts diagrams we designed yesterday, everything could be a box. A decision could be a box. A speak action could be a box. Everything could be a box. This means that when we look at the diagram, we don't extract that much information, so everything looks the same. Everything looks like a box. And then we have to be looking at each individual node to decide what it is. Is it a decision? Is it an action? Now, what we did by representing decisions as diamonds, we just make them very quickly identifiable without having to look into the detail. If I show you a flowchart diagram and I ask you how many decisions there are there, you can answer very quickly. It wouldn't be that quick if we had to go through each one of them. So this is what that principle says, that every concept in the language should ideally have some sort of different symbol. In this regard, the diagram I showed you was not great because we had 3 different types of actions and all of them looked like rectangles, right? So you could not very easily discriminate between speak actions and input actions and redirect actions, right? A good graphical syntax would make that easy to distinguish. Now, what happens if we have a concept for which there's no symbol? We call that a symbol deficit. It means that we cannot instantiate that concept graphically in our diagram. Symbol redundancy happens when, for the same concept, we have 2 different representations, and that can create some confusion when you look at the diagram. On the flip side, we can have symbol overload, and this is what we had in our language, because we had more than one concept mapped to a rectangle. Right? And then a less common issue is that of symbol excess, where we have something in our diagram that doesn't correspond to anything in our model, to no concepts of our modeling language. So the idea is to try to aim for a one-to-one mapping, not to have redundancy, not to have overload, but just to have a clear mapping between concepts and diagram elements. Now, the second principle is to maximize the perceptual discriminability. And this means that, well, we could have different symbols for our actions and our decisions. And they could differ in shape, but shape is only one of the retinal variables. So if they varied both in terms of shape and color, that would be even better, because they would be even easier to distinguish. And we have 8 parameters here, so we can play with shapes, we can play with sizes, we can play with colors, textures, orientation, brightness, and then the horizontal and vertical position of diagram elements, right? And these all contribute to them being visually unique and easy to identify. Okay, so with that in mind, which of these two syntaxes are more effective, would you think? And why? Okay, so who says the first one? Okay, why?
Because all of them are different, so it's easy to.
Mm-hmm. So the first one, because all of them are different. So this one.
And there is no partition in like process and data like the second one, which is maybe excessive symbol.
So you're saying that this one has excessive symbol. So first of all, this one has the same symbol
As the first one. Yeah.
for these two concepts, for a data store and for external entity, which is not great. I mean, this one is not doing much better, but at least it has this separator here. So there is a visual distinction. It would have been better if process here perhaps was a circle, because that's, again, more distinguishable than just a rounded rectangle where you have to look at the corners to decide if this is an entity or a process. But then again, you get this line over here, which clears things up a little bit. So it's this sort of syntax, this sort of design decisions that you should be avoiding when you're making concrete syntaxes, when you're making diagrammatic syntaxes for your languages. By default, graphical modeling frameworks will just kind of make everything a gray rectangle. And this is where you need to start putting the effort to produce symbols that make sense and that are easy to distinguish between each other. Okay, the third principle is called semantic transparency, and this refers to the extent to which the meaning of a symbol is intuitive and it can be inferred from its appearance. So here, for example, just by looking at this shape, you can tell that A either precedes B or it causes B, right? This is without knowing anything about what this language is. That's the natural interpretation. Now, if for some reason I had designed my graphical syntax to mean that B is before A, right, and this is entirely possible, then that would be really confusing, right? That would create mental overload in order to remember that, well, when I see this arrow, it actually means the opposite thing from what I think it means. The same goes with subclassing or subset. So compartments, spatial containment is a very intuitive way to show belonging, to show things like a subset relationship. Spatial overlap can show intersection, and then positioning something above something else tends to show hierarchy, right? And again, it would be very confusing if B was the manager of A, right? We don't have to stick to symbols only. We don't have to stick to like squares and circles, etc. We can also use icons. And icons can carry a lot of information. So we can stick a little icon, for example, here in the corner of these icons, and that will make them much easier to, these shapes, and we can make them much easier to discriminate. Okay, if we know one thing about diagrams, and maybe the reason why many of us kind of dislike diagrams to some extent is because they don't scale very well. If you create a UML class diagram with 50 classes, you kind of spend more than 50% of your time trying to take the lines, like playing Snake, and minimize the overlap between nodes and lines and stuff like that. And this is terrible. I mean, these diagrams are unmaintainable because if someone asks you to, put another box somewhere here, it's a good reason to quit your job and start find something else to do. But this is because we don't treat diagrams right. There's no reason why we should have so much information on one diagram in the first place. A diagram should have up to 9 elements, roughly speaking. If we need more complex structures, we can use things such as hierarchy and modularization. We can use things like sub-diagrams. We can have a top-level diagram, and then we can double-click on a node. We can go to the next level of detail and the next level of detail, and so on and so forth. There's really no reason to try to put everything in one diagram. I think the reason why we intuitively try to do that is because of the tools we are used to using. If you use like drawing tools, they don't normally have this concept of a sub-diagram, so you have to do your best to fit everything in one picture. Modeling tools, on the other hand, they provide sub-diagrams. Modeling frameworks provide support for sub-diagrams for your own domain-specific languages. So it's a feature that you need to seriously think about using every time you're designing a domain-specific language, which will be used to construct models of more than 10, 20 elements. And we'll see how we can achieve this in GMF, in the Eclipse graphical modeling framework. Another principle that we need to keep in mind and that we need to follow where possible is the complementarity of text and graphics. So we said that graphics, shapes, etc., they're easier to discriminate, and we should prefer them where possible. This doesn't mean that text is useless. Actually, putting text and graphics together is much more effective than using one of them. So here we can see examples that combine text and graphics. We have this graphics-only approach where we show this one-to-many relationship using this chicken foot symbol over here. We have the same, but with just a textual encoding, so we don't differentiate in terms of the lines, but we just specify multiplicity here. And you can see how it's much more clear what's going on here because the one reinforces the other. So if you were not really sure what that chicken foot symbol means, now you know. Right now you can tell that it probably means many. So yes, combining text and graphics is a good idea. Now, the fact that we can differentiate and we can create all sorts of symbols with all sorts of colors and shapes, etc., it doesn't mean that we should turn out domain-specific syntax into a carnival, right? We need to think about graphic economy. We need to think about the fact that a person can only keep so many combinations of colors and shapes, and they're kind of mapping to concepts in their head. So we need to kind of constrain ourselves and not go wild. Otherwise, you end up with something extremely colorful that is very hard to understand. Okay. So there are other graphical design principles that we won't go into in this lecture, but I strongly encourage you to read this paper called The Physics of Notations, which was the paper that introduced these principles in the first instance, and read more about the remaining 3 principles. Okay, so enough with the theory part. This is something you should keep in mind when you design your graphical syntaxes. Now we're going to talk about how you design graphical syntaxes. What tools do we use, and what is the output we should expect? And in particular, we're going to start with the Eclipse modeling, with the Eclipse graphical modeling framework. So So yesterday we talked about how to create meta models with EMF and how to then create models that conform to these meta models. And if you have any software development experience at the back of your head, you might be thinking, like, why do we need all that, right? I could capture this information in a JSON file or in a YAML file or in an XML file. If I wanted to organize a conference or whatever, or to organize these research projects, I could just have my XML file and I could type in all the partners and the work packages and everything. Why do I need Eclipse? Why do I need to know all of that stuff? And the main reason is because EMF is really the foundation of a larger ecosystem of technologies. So, for example, if you were to use XML or JSON or YAML to capture this information about your conference or about your grant proposal, then if at some point you wanted to add a graphical modeling interface on top of it, you would be pretty much on your own, right? You would have to rediscover, essentially reinvent the wheel, find a graphical, like a JavaScript library, and then try to make it fit with your underlying XML document, so that whenever you change your document, your diagram is updated, or vice versa. Then at some point, you would come up with a need for model validation. So not everything that you type into your XML document or your JSON document is valid. So you would need to write some validation rules. And again, you'd have to take a third generation programming language, just improvise again, write your validation rules in some shape or form. By starting with EMF, when you need these capabilities, there are existing frameworks that you can start leveraging, and you can get this functionality at a very, very low price. And I don't mean monetary price, I mean in terms of effort. So you will see how easy it is to literally, with 5 lines of code, to create a fully fledged graphical editor for a flowchart-based language using GMF and Eugenia. And good luck trying to do that with a technology that hasn't been built for that purpose. Okay. So GMF is a framework that sits on top of EMF, and it supports the development of diagram-based editors for models conforming to eCore meta models. So yesterday we saw how we can generate from an eCore meta model, how we can generate a tree-based editor, which we can use to create our models. Today we're going to see how we can generate a diagram-based editor that we can use to do the same, right? So we'll end up with exactly the same models, just a different environment for constructing them. GMF works in a generative manner. So we saw that in EMF, you could register your meta model, and in the same workspace, you could create instances of it. That doesn't work in GMF. You have to generate code. You have to generate code. You have to launch a new instance of Eclipse, and your graphical editor will be there waiting for you. So what should you expect out of GMF? This is like Eclipse, your regular views, your project explorer, your properties view. What we get out of GMF is a new dedicated editor with all the concepts of our language in a palette on the right-hand side. And then we can drag and drop them. And then when we select them, we can go and change their properties here, right? So from GMF, we'll get the editor, we'll get a new file wizard, we will get a dedicated extension for our diagrams, and lots of other goodies. And all that comes almost for free, as we will see. Okay, so thinking about our meta model from yesterday, about our flowchart meta model, we don't have quite enough information in it to generate a graphical editor. We don't, so in our meta model, actions and decisions and transitions are classes. We don't say anywhere that actions and decisions should be visualized as nodes, while transitions should be visualized as edges. This information is nowhere in the meta model itself. It's just in our head. We don't also specify that the root concept is a flowchart, right? We said that we need in EMF, we need to introduce that kind of root class for our meta model, and in the case of our meta model, it was the flowchart class that contains all the states and that contains all the actions and the transitions and everything. But we don't state that anywhere in the meta model itself. So in order for GMF to be able to generate this nice editor, it needs additional information. So what should each E-class be visualized as a node, as a connection? If we have labels, where should they be? Should they be internally to the node? Should they be externally to the nodes? If we have a containment reference, should be visualized as a link? Should it be visualized as a spatial containment in the form of a compartment? So there's a lot of information that we don't actually have in the model and that we would need for GMF to generate a graphical editor. So in order to add this information, GMF provides 3 models. These are regular EMF models, so you can open them with the EMF tree editor, and you can edit them. We'll see examples of how they look in practice. The first one, the GMF graph model, defines all the shapes involved in the editor. So this is where we can create our rectangles with like fancy borders and shadows and background colors and gradients and so on and so forth. This just defines shapes, right? It doesn't link them to the concepts of our language. It's just a drawing tool with a terrible tree-based interface. Now, the GMF tool model, that's the second model that complements our meta model, and here's where we define the tools for the editor palette. So there's where we define what tools we will see in our editor palette, like action, decision, subflow, trigger, etc., but also how they will be grouped in folders, right? So this is quite a simple model. And then finally, we have a GMF map model, which really maps graphical elements, so shapes that we created in our GMF graph model, with actual classes in our meta model. So it says that this nice rectangle, it actually maps to an action. And it also maps tools in the palette to E-classes, so that when we drag an instance of action, a new action is created in our editor. As I said, constructing these models is not an easy job, because you have to. So GMF only provides tree-based editors for these, and there's a good reason for that. It's because these are very complex models. So when you right-click for a new child to a node, you will see that you get like a screen-long list of options. It would be very, very hard to have a graphical syntax for this. So you don't get a lot of support when you're actually trying to create these models, and these are quite complex and interconnected, and there are all sorts of things that can go wrong. You can forget to set a property of something, and then it just crashes, or you get a compile time error when you generate. So once we have these 3 models, the graph, the tool, and the mapping model, GMF has a model-to-model transformation that takes all of these and the meta model and produces a generator model. And this has a GMF gen suffix, and this contains all the information that GMF needs in order to generate lots of Java code that implements the editor. Then the final step is for a model-to-text transformation to consume that GMF gen and actually produce the code. And this comes in the form of a new Eclipse plugin. So you will see that we had yesterday, when we generated code from our meta model, we ended up with 4 Eclipse plugins. We had our flowchart plugin, a flowchart.edit, a flowchart.editor, some tests. Now we'll also get a flowchart.diagram, separate project that holds the GMF editor. So as I hinted, these GMF specific models are quite hard to get right. The meta models of the GMF graph and the GMF map models are quite big. And if you get things wrong, when things work, they work fine. But when they don't, when you forget something or when you get something wrong, you get either incomprehensible errors when you try to generate your code, the generator breaks at some point, or you just get compilation errors in your Java, and it's quite hard to work them back to what you did wrong with your models. Plus, if you modify your eCore meta model, because these are separate models, then you will need to remember how these other models map to your meta model and go and update these manually. So, not all hope is lost, because there is a tool that sits on top of GMF, and it makes life easier for I don't know, 90% of the editors you will want to build. So that tool is called Eugenia, and it works by instead of using these extra models to attach information about what is a node and what is an edge and what is the border color of that node, etc. It uses annotations which are embedded in the meta model. So now instead of having information scattered across 4 artifacts and 5 artifacts, if you think of the GMF generator model, all the information about your editor is in one file in the meta model itself. So Eugenia kind of centralizes this information in the meta model, and it also provides a set of validation constraints that catch common errors. So you get sensible error messages as opposed to compilation errors in the Java code. Of course, Eugenia sits on top of GMF. It doesn't replicate it. And therefore, from these annotations, it automatically produces these GMF graph, GMF map, and GMF tool models. And then it hands over to GMF to do what it knows best and to produce the final code. OK, so this is our meta model, and I've added Eugenia annotations. So just ignore them for now. What we had was a class flowchart, which had the number of nodes and the number of transitions. And then we had our nodes with a label and incoming and outgoing transitions. And then we had actions and decisions, which extend the node. And then in our meta model, the one we created yesterday, we also had subtypes of actions. We had 3 different subtypes of action. OK, so what we are adding with Eugenia is just these blue lines, right? So first of all, we annotate the flowchart class using this gmf.diagram annotation, and that marks that class as the container of everything in our model. Then we specify that nodes, that instances of the node class, will actually be visualized as nodes in our graphical editor. And they will have a label which will reflect the value of their label property here. And then we also specify that transitions will be visualized as links, as connections in our graphical editor. They will have a label that reflects the value of their label property. They will have, and then their source will be the value of their source property, and their target will be the value of their target property. And this is pretty much all the information we need to provide in order to get a fully functional graphical editor out of our language. So these are only 2 or 3 of the annotations provided by Eugenia. There is an extensive tutorial under the Epsilon website. And this is where you will find all the different annotations supported for classes, for references, for attributes, and so on and so forth. So that's pretty much everything. That's all the information we need to provide to our meta model. Then we can generate an editor. And here is, I think, where I switch to a live demo. Okay, so let's go back to our meta model from yesterday. So in our meta model, we call the container model, not flowchart, right? I will add an @gmf.diagram annotation to it, and that means that this is now our canvas, that the model is a canvas. So a link we will visualize as a gmf.link, and well, this is confusing, so what I'll do is I'll change this from source and target into from and to, and I will also add a text attribute, so we'll have to change this as well to from and to for consistency. Okay, so a link, instances of the link class, which just happens to be called the link. I think we actually changed this yesterday to show you how the EMF editor responds when we actually break things. So I'll just change this to transition again. Yeah, these are not good names. Okay. So transitions are visualized as links, and they have a label, which is the text, right? So this is the value of the text property of the transition, and the source of the link is the from reference of the transition, and the target is the to reference. Okay. And then steps. So all the steps, actions, decisions, speak actions, and so on and so forth, I will just mark as nodes for now. So all steps are nodes that have a label that reflects the value of their text property. And annotations in Eugenia are inherited. So because action extends step, it will also be marked as a node unless we override this, unless we specify something else. Okay, I think that's pretty much it. So with these 3 lines of extra information, I can now right-click and go Eugenia, generate GMF editor. And you will see these 3 models that I mentioned before, the GMF graph, the GMF map, and the GMF tool models. While GMF is doing its thing, I will just open them so that you can see what goes in here. So here we have one figure for every concept in our meta model, a decision, a speak action, a redirect action. If you look at the figures, all of them are rounded rectangles at the moment. They have a certain margin with certain insets. And these are models generated from Eugenia by these annotations that we specify. This is the default that Eugenia produces. Now, what else could we add here? Lots and lots of things, right? So GMF offers a very rich meta model for designing shapes and very complex and composite shapes, and you can have labels in certain parts of these shapes, and they can be exposed as top-level references, etc. You can do very, very complicated things with GMF. And then we get the map model that says that, well, let's go to properties. That says that a speak action is actually mapped to the speak action node, which we specified in our graph model, right? So this is what does the mapping, and it also is also mapped to this creation tool, which lives in our GMF tool model. So here you can see the 2 folders, the 2 groups of tools that appear in our palette, objects and connections, and then the different tools that are in these 2 folders, right? Okay, I distracted your attention, and while you've been looking at these models, this diagram project has been generated, which holds the code to our editor, to our graphical editor. So now I can right-click and say, run this again as an Eclipse application. Okay. And what I'll do is I will create a new other. See, before we had this new flowchart model entry in our new file dialog. Now we also have this flowchart diagram option. Okay, so I'll leave the name as is. You see that the extension is flowchart_diagram. It's whatever the extension of our abstract syntax is, _diagram by default. But then again, you can change that. And we'll just finish. See, in this case, I didn't need to choose what is the root object of my model, because I've actually specified this in the meta model. We set a class as GMF diagram. Okay, so now I can start creating models. And I create decisions. And I can create transitions between them. Right? And I can replicate the enter your account number. Yes. Okay, now if I select an element here and I go to the properties view, you can see how I can populate its properties as I could do in the tree editor. Now, if you look closely, when I created my diagram, another file was created. So I have this default flowchart diagram, which is what I created, but also this default.flowchart, which is a file that was created in the background. And this is because by default, GMF keeps the abstract model from the layout information separately, in separate files. So I can open my .flowchart model, and this is where all the semantic information is kept, my actions, my decisions, my transitions, etc. If we open the flowchart diagram with a text editor, unsurprisingly, it's XMI again. And then if we look a bit more closely, what happens here is here we have our speak action node. So this one is the persisted representation of this one here. If you look at it, what's going on? Well, it says that it's a shape, it has a certain font name, and so on and so forth. It is of type decoration node, which we don't care about. But then it has this element here, and it says that this is actually a link to an element in the default.flowchart model. So the diagram doesn't replicate the information in the model, it just links to it, right? Which means that if I was to go and change this model, and let's say bank 1, and open my diagram again, we would see the updated value here, because that information is not stored in the diagram, it's only stored in the model. The diagram only stores where this rectangle is, and if we have like bend points in connections, etc. It doesn't hold any semantic information, which means that we can, when we are actually writing our code generators or our model validation, we can ignore the diagram. The diagram doesn't have any useful information for us. All the semantic information lives in the model here. Okay. So what else could I demonstrate? Yes, let's do a little bit of customization. So every time I change my meta model, I will need to regenerate my GMF code, which means that I will need to restart my Eclipse. So I'm exiting this new Eclipse and I'm going to modify the meta model. Now, I said that it's a good idea to try to break down your models, your diagrams into sub-diagrams so that you don't end up with these huge spaghetti diagrams. How do we do this? First of all, our abstract syntax needs to accommodate this, so we need to have some notion of like sub-models, sub-flowcharts, sub-packages, sub-systems, whatever. So what I'll do is I will add a containment reference called sub-models, which is of type model. And here I will say that the model is both a diagram and a node. And what else do I need to say? And also, a model extends step so that we can create another step, which is really just a link to a submodel. Okay. Let's rerun our generator. Okay, and run a new instance of Eclipse. Okay, so if we open our diagram again, so I could add another model here that says manage existing customers. And I could delete this one, right? And I could have another model that says manage new customers. And we can have a transition here. Transition says yes. Another transition that says no. And then if we double click this one, it will open a new diagram where we can create more actions and more transitions, right? And we don't have to try to fit everything in the same diagram. So here we could have an input action that says, please enter your account number. I can close this diagram, and when I double click this again, it's still here waiting for me. Okay, so the complexity of the model is not a good reason to have a complex diagram, right? You can have many diagrams, and here I could have yet another model that says, like, manage premium customers if I wanted to add more. So we could start with a decision, for example, and say, are you a premium customer? No. Yes. And then I could have a separate sub-diagram for my premium customers. Okay? And it can go all the way down to handle all all the detail I may want to have in my model. Now another thing is that not all the information in a modeling language needs to live in the diagram, right? You may have, for example, here in your meta model, if you were to generate code, where's the meta model? Here, if you eventually want to generate code from these models of yours, you may have a lot of information. So you may have some configuration elements that you don't really want to have in your model. So, for example, in your input action, in your speak action, you could have a class character in your model, and the character could have name and okay, let's just stay here, and then that they could be male or female. So okay, so we could change our, so where we have voice here, we could have a reference to, let's call this, yes, character. I think character is a reserved word. Let's call this bot. So it can have a reference to a bot called the bot that actually speaks this out, and maybe they can say, well, hi, my name is so and so, and then say what they need to say. So here we need to have our bots here. Okay, and maybe bot is something that we don't want to show on the diagram, right? We don't want to show all the information, all the elements in the diagram. That's absolutely fine. Let's generate our editor again. Let me close this bit. So run a new Eclipse instance. Okay, so what we want to do here now is, there's no way to create a bot in our diagram. That doesn't mean that we cannot have it in our model. I'll just close these to create a bit more space, and I'll just put these side by side. Yes. So here I can go to my model, and I can create a bot here. It doesn't have a graphical syntax, but still I can instantiate it in my model, and I can say that this bot is Bob, and it's male. Now when I go to my action here, you can see a bot reference. I can select Bob, and that's fine, right? Not all in the information in our model needs to live also on the diagram when we have a diagrammatic syntax. Any questions? You all need desperately coffee. I need desperately coffee. Okay, let's break for 10 minutes and we'll continue with more GMF. So in my slides I said that icons are also very nice, very useful in order to distinguish between different concepts in our graphical syntax. So if you look at our current graphical syntax, it's quite boring. So everything is a rectangle, everything is a white rectangle with a kind of grace border. So let's customize our editor a little bit. What I'm going to do is first I'm going to replace this auto-generated icon with something more meaningful, more representative of a speak action, and I'm also going to change maybe the color of these nodes so that decisions are kind of stand out. Okay, so changing the icon of a concept is quite straightforward. If you go to your generated code, under the .edit plugin, you will find a folder called icons. And then if you follow it all the way down to object 16, here are some auto-generated icons that EMF has produced for us. So changing the icon for, say, speak action, if I double-click speak action, you'll see this kind of generic icon here. It's just a matter of finding a new icon. I have downloaded one here, and just putting it in this folder, overwriting the old icon. So now, again, I will need to close and restart my Eclipse. But when this happens, you will see how the default icon has been replaced with this nice custom icon, and it will already kind of make it a small difference in our editor. So you can see we have this nice icon now, and it also appears in the palette, right? So you could use something like, I don't know, Font Awesome, and have a consistent set of icons for the different concepts of your language. Okay, let's customize. Let's change the color of decision nodes as well. So of course I don't remember all of these annotations by heart, so we'll need to go to the GMF tutorial under the Epsilon website, and this has a small annotated meta model, and that produces an editor, and then it also lists all the different annotations that Eugenia supports. So for example, well, we have this GMF diagram annotation, which we use without any details, without any values, but we could have a diagram.extension value in there that changes the default diagram extension. We could have this one file property that tells GMF to put the diagram and the file and the abstract model into one file, so that we don't have these two files, but everything lives under one file. We can ask it to generate an RCP, like a standalone application, as opposed to an Eclipse plugin, and so on and so forth. So for nodes, we can change the border color, we can change the border style, the width, and so on and so forth. What we are interested in changing is the actual color. Okay, so I'm going to go and add to my decision class, I'm going to add an add.gmf node annotation and say that the color, we use American, yes, American spelling. So the color is I will put an RGB value here. Okay, so if we generate our editor again, and run a new instance of Eclipse. Well, this existing node has not been affected, but if we create a new decision node, it takes the color that we specified. The generated editors that GMF produce also support kind of changing the appearance of individual elements. If we wanted to change the font size or the color of an individual element, we can do that. So here we can go and change the color and say, well, this one's green, right? And this information only lives in the diagram. Okay, so this is icons for you. Yes. Shapes, yes, of course. Let's do shapes. So where is shapes? Shape. I think it's called figure. Yes. So figure where you can have a rectangle, an ellipse, a rounded rectangle, or an SVG file. So you can draw your own shape using a drawing tool. You can export the result as an SVG, as a scalable vector graphic, and you can use that to represent the symbol on your editor. So for now, let's just change it to ellipse so that we don't have to create a new SVG. So if we wanted to create a diamond, for example, SVG would be a good approach. There's also this polygon where we can specify a list of points, and it can create any polygon for us. Or we could go to Java, and we could implement a Java class that implements an interface that GMF provides, which is called figure, and then we can go crazy. We can use Java to draw any kind of shape we want. So for now, I'll just change, say, this one to be an ellipse. And regenerate our editor. Oh, also, the GMF code can be extended. You can actually go in and change the GMF code, and it uses the same mechanism, that generated not mechanism, to preserve changes. So here you see how our decision has changed into an ellipse now. And if you're worried about like the position of the label, if we go to there's a Eugenia article here that would tell you how to create like a middle layout, so that the labels appear in the middle of shapes as opposed to the top left corner, which is what happens by default. Okay, you can also have nodes with images defined at runtime. So, of course, now things start getting a little bit more involved, but you could have, every time you change the property of an element, its image could change, right? For example, if you had a concept called traffic light and it was green, amber, or red, and you change that property, then the icon of the traffic light could change on your editor, right? And this article shows you how to do that. What have we not talked about? Okay, we haven't talked about compartments. Compartments are also quite useful. So compartments are used to visualize spatial containment in GMF. So let's say that, let's go back to our meta model and say that in our input action, currently we have this string variable. So this is what this particular action will ask from the user. If we wanted to have, if we want to make this a little bit more elaborate, we could actually have a class variable, which would have a attribute string name and an attribute string description, so that the system could tell to the user, well, give me your account number, and press star if you don't understand what account number is, and then if the user pressed star, it would read out the description of account number to say, well, it's the long number, the first side of your card that has 16 numbers, whatever. And we could have an input action that actually asks for more than one thing in one go. So in this case, with no longer having a single attribute, it's no longer sufficient. We'll have a val, a containment reference to objects of type variable. And what we can do, yes?
Why is it not a reference?
Because we want that input action to own all these variables. It's a design decision. right? And what we want to do, if we go back to our editor, is we want to extend let's create an input action. We want to extend this box here with a compartment inside where we can put in variable objects, right? And then as long as the variables are contained within this box, they belong to this action. If we move them to another input action, they get moved to the other input action object. So what I'm going to do is I'm going to add a compartment here. I'm going to say that this reference is visualized as a GMF compartment. And actually, if we look at the details of compartment, we can specify whether it's collapsible or not, whether we can show and hide these inner nodes or whether they are always visible. And we can specify the layout of this compartment, whether we can move things around in the compartment or whether we actually get a fixed list. So we'll just go for a, let's go with a free layout. That's fine. Actually, I'm going to add another property here and demonstrate two things in one go. So I'm going to go to variable and say that a variable also has a type, which could be integer or string, so that the system knows how they can validate the input that they get from the user. And we won't do anything with this right now. Anyway, so we have our compartment. We can generate our code again. I'll need to go and close my editor here. It's generating. And I'll go and run my application yet again. Okay. It's not going to work because I haven't really said here that a variable is a node, right? We need to specify that a variable is visualized as a node. So I'm going to kill this before it breaks. I'm going to say here that, well, actually, this one is a node and it has a label which reflects its name attribute. Fine. Eugenia, generate code. I mean, if you feel that this is kind of getting a little bit boring, we have to generate the code and we have to run the code. I mean, you wouldn't want to write that sort of code, right? So you just have to wait a little bit, and that code gets generated all for you. Also, the newer instances, so Eclipse, the Eclipse people have done a lot of good work over the last year in terms of starting up performance. So the latest versions of Eclipse will run in like a very, very few seconds. So you don't get to spend as much time looking at this plus screen. And also, this is a 6 years old computer. Okay, good. So I will create an input action, and you can see now how you can see anything that you will see, right? So you can see how now we have this extra compartment here, where I can create variable objects. Okay, and this spatial containment relationship is translated into a containment relationship in my model. So if we look at the flowchart, so we have our input action and it contains these two variables, right? Now, if I was to create another input action here, and to move one of these variables in here, save, you can see how it's actually moved in the abstract syntax tree as well, right? So this spatial containment has semantics. It's not just placement of elements on a graph. Good. Now, one more thing, we can have more complex labels, right? Right now, all our labels just represent the value of a single attribute, but we can have more complex labels using patterns. So if I go back, I will just close this. If I go back to the documentation, so in GMF node, right, we can have a label dot pattern, and we can use this sort of format. So we could say, could go to our meta model and say that actually the label for a variable is not name, it's name and type, and then the pattern is this one. So it's the name followed by a colon followed by the type. So if we were to generate our editor again, and run again a new instance of Eclipse, so here we could say that, well, pin is a string, and you can see how by doing that the type property of our variable has also been modified, and it's now a string. So we can have complex labels. We don't have to just use a single attribute for the label of a node. Okay, so that's that. Any other interesting annotations? Yeah, so we can have, so here I've demonstrated so far how we can have e-classes, how we can have classes that are annotated as links, right? But we can also have references which are annotated as links. So now I'm going to change my meta model and actually not use containment for variables. I'm going to change this to a ref as you suggested, right? So I'm changing this to a ref. This can no longer be a compartment because these are not owned, so I'll have to get rid of that. And now variables need to be contained somewhere, right? Because they can no longer be contained under input action. So I'll need to go here and say, well, all my variables live here. And I'm starting to push GMF, and at some point it will start producing compilation errors here, and we'll have to delete the generated code and run it again. But let's try once more. Okay, yes, and I have forgotten. So here, now what we want to do, because we cannot contain variables within input actions, we want to link to them. So then we can annotate this reference as GMF link. That will just create a link. And then we can say that the target decoration is an arrow. Okay, so I'll generate my editor again. Okay. see, right now I'm starting to get compilation errors in my generated code because GMF will never delete code, right? It's very conservative. It will never delete code that it has generated. So when you start switching things around, you may end up with obsolete code that just creates compilation errors. That's absolutely fine. This is all generated code, so we're fine to just completely delete it and delete it from disk as well. Because when you delete a project from Eclipse, it only removes it from the workspace, but the actual source files remain unless you tick this box that says, well, actually delete it from disk. Okay, fine. And then let's regenerate our fresh code. And errors might occur. You might get compilation errors everywhere here, right? Because EMF doesn't also delete code. But the only real artifact we care about is this one. Is this 67 lines of emphatic code. Everything else is generated. So you can literally take that, put it in another folder, clear your workspace, create a new project, and you're ready to go. Okay, so the GMF generator has run again. And now we don't have any more compilation errors here, which is nice. So I'll run a new Eclipse application. Right, so this has messed up my diagram because there's no longer a compartment here. So the GMF editor complains gracefully. So I will get rid of, I will close this for now. Now, also what has happened is if I open my flowchart, are the variables still here? Yes, they are here, but EMF is just ignoring them. Okay, again, the fact that we are using a text-based notation to store our models is convenient. So I've just got rid of the two actions, and I will actually delete my diagram, right? And I will use the auto-generated wizard that GMF has produced that allows me to create a new diagram from a model. And it will produce some horrible layout, right? But that's fine. Well, not so horrible in this case. Right? That creates, that maps the elements in the model into a diagram. So now I can create my variables on the canvas. Say this is a pin of type string. And because I've said here that the input action has a link to variables, you can see that this translates to a connection here. I can click it and I say this input looks at this variable, this input also looks at this variable, and now that's fine because this is not a containment relationship, so we can have multiple input actions working with the same variables. So this is a GMF link that applies to an E-class. This is a GMF link that applies to a reference, that visualizes a reference. Okay, any questions so far? Anything else you'd like to try? Yes?
Is like we are coming from a text-based meta model to a format like that editor.
Mm-hmm.
Is there a way around like starting from the format or something like generate that meta model? Or
Generate what? But this is an instance. This is an instance of your editor, right? So these are two different meta levels. So this is your language. So this is your language, and this is a model that is an instance of that language, right?
Okay.
And you need the former before you create the latter. It doesn't make sense. It's not like going back. It's not back and forth. It's up and down, right?
Yeah. So there is no way we can have a metamodel generated, not from this kind of scenario where you have to have a metamodel in order to generate an instance, which is this portion. Is there a way of having a metamodel, not text-based, like?
Yes. I mean, we could do exactly the same work using this tree editor, right? And we could add our annotations here, and we could add our everything here, right? Emphatic is just a convenience textual notation. I just find it easier to type in metamodels rather than to go right-click, new child, attribute, go to the properties view, change the type, etc. And you could also generate an E-core diagram. Right? And you could have all your classes here, and you could edit them in a visual way. Again, for meta modeling, I'm just finding it easier to type things in. But yes, there are options. And again, these are all benefits from the fact that all of these tools work on top of EMF. So this is not part, this editor is actually not part of EMF. It's part of another tool that just works on top of EMF. Any other questions? No? Okay. Yes.
Just to so if we do any changes in E-core or EMF, so we need to generate the GMF file again.
Yes.
After.
Yes. And we can do this. So far I've been doing this from the EMF model. So I've been right-clicking in Eugenia, generate GMF editor. If you decide to work with your E-core file directly, you get the same option here. Right? So you could, if you just don't like text-based syntaxes, you can just work with a tree editor or with a diagram editor, and you can run Eugenia from your E-core file. You get all the options again here. Any other questions? Nope. Okay, so I think I'll change chargers because this is about to die. Okay, right. So, so you will find instructions, you will find screenshots for doing all of that in the slides. So that you don't have to remember these menus of heart. So you can see how we can right-click in the emphatic file and generate a GMF editor, and we can run a new application. We can create a new diagram, and then we can start putting things on the diagram. So I put these screenshots in the slides for the practical in the afternoon. Okay, so I've been very careful in this demo to kind of show you the things that Eugenia supports. There are many things that Eugenia doesn't support. GMF is very, very complex, right? And Eugenia doesn't mirror its complexity. Because if it did, then we would end up with an equally complex set of annotations and details, etc. And that's not the point of Eugenia. It's to simplify like to get you up to the 80% of your editor, and then you can tweak these models and you can fine-tune the appearance of the generated editor using GMF mechanisms. So let's try to do something that Eugenia doesn't support. For example, we might want to change the font style of decisions and make that a bold label, right? Eugenia doesn't support that. So what would you do in this case? You would need to go back to your graph file, right, where we define all the shapes. These shapes have been generated by Eugenia. And we need to go to the decision figure. We need to go to this label here and go right-click, new child, basic font, and then go to the style and turn that to bold. So now if we rerun Eugenia, that change will be lost, right? Because Eugenia will just regenerate all the models on top of it. It will lose this change. We don't want that. So for now, we'll just follow the GMF workflow itself. So we won't invoke Eugenia. We will go to the GMF map model and say, create that generator model, that GMF gen, that GMF expects. And then from our GMF gen model, we will just run the diagram generation code, right? So we're leaving Eugenia out, and now we've started modifying the generated models, so we're back to the GMF workflow. We've lost that part.
It means that we can't come back anymore?
We will come back, yes. There's a twist. Okay, so let's run our Eclipse application. Of course, we have to stop the previous one before we do that. Okay, so now you can see how these labels have a bold font, right? Which is nice. It's what we wanted to do, and there's a lot more customization we could do. You know, if you see, we could change the foreground color of just the label, and again, Eugenia doesn't provide an annotation for that. We could change the margin of the label, or you know, whatever. And Eugenia doesn't know about any of these. Now the problem is that, as Jean-Marie pointed out, now we are on our own, right? We have changed the generated models. If there's no way to go back to Eugenia, it means that if we now make a change to our meta model, we'll have to change all these GMF models manually, and we have to go and create new figures and new labels and all horrible stuff that we wouldn't want to do. So what Eugenia supports in order to handle such cases is the concept of a polishing transformation. So Eugenia is essentially a big model-to-model transformation, and we will talk about the model-to-model transformations tomorrow. So it's a transformation that takes a meta model, an annotated meta model as input, and produces these three models as output. So it also supports this concept of polishing transformations, which are scripts essentially that run after the execution of the built-in model-to-model transformation to customize these generated models in a programmatic way. So what I'm going to do here is I'm going to create a new file called ecore.gmf.eol. EOL is the core language of Epsilon. It's a small programming language for interacting with models. Eugenia recognizes, it actually looks, when it's executed, it looks for a file called ecore to gmf.eol, which sits next to the meta model on which we invoke it. And if it finds it, it will run it after its built-in transformation. So what we want to do here is we want to programmatically change this model to add this new font, right? In order to do that, we need to first of all get hold of this label object. I will open this model using another editor. I'm going to actually open it using Exceed. That's the reflective editor we were using yesterday. So here I have my decision figure, and here I have my label. So in Exceed, we can turn on this structural info flag, and then that will tell us for every model element what type it is and where it is contained. So it will extend the label and it will provide more information. So here we are looking for a label called decision label figure. So I'll go to my UL file and I say that the label of interest is from the GMF graph model. It's a label that has the name decision label figure. Decision label figure. Fine. And what I want to do is I want to create a new basic font. If I look here, what I created here is a basic font, right? And then I want to send the style of this font to bold. Now, how do I know all of that stuff? If I look at the properties view, what I've changed here is a property called style. This is an enumeration. How do I know what are the literals of this enumeration? Well, if you click here, it's bold, italic, and normal. Okay. So what Eugenia will do is the next time I run it, it will just generate its default models, and then it will run this small script on top of them, which means that it will add this font and it will change its style every time. So what I did here manually by pointing and clicking, I've just automated here using a small script that will be applied every time the transformation runs. So now I'm fine to rerun Eugenia. Whatever. No. I don't want this diagram. So just rerun Eugenia. I'll close this. Run it again. If I create a decision, again it gets a bold font, right? And this is because of the change that was applied to my GMF graph model through this polishing transformation. And we call it the polishing transformation because the built-in Eugenia transformation produces like a rough editor where we cannot customize lots of aspects, and then with these polishing transformations we kind of fine-tune the details and we get the editor to the exact state that we wanted to. And this is quite nice because in these transformations we have full access to all the GMF metamodels, the GMF graph metamodel, the GMF gen metamodel, the GMF tool metamodel. So anything we can do manually, any editor we can create manually using GMF, we can also create using Eugenia. But instead of making changes to these models manually, we do this programmatically. Yeah, go ahead.
So if we should not change something that is concerned by the transformation.
So if you delete, for example, the decision, if you rename the decision to choice, whatever, then you would need to go and change this code as well. But you will be forced to, because if you actually do that when Eugenia runs, it will produce a runtime error here because that will be null. So you will know that something's not right. In many cases, in some cases, it may just silently not do what you wanted to do. This means that you can also create so because these transformations also have access to the meta model, you could also introduce your own Eugenia annotations. And you could consume these annotations in here to do things in a batch mode. So you could introduce your own annotations and say that right? This has no semantics for Eugenia, but then here you could say for every class what did I say? Big margin. Then do something, right? Change the respective shapes and so on and so forth. And this is how we have grown Eugenia over the years organically. So annotations that we tend to repeat a lot in polishing transformations, they just make their way into the core of Eugenia. Yes?
Is equal to GMF a specific name?
It is, yes. Eugenia will just look for a file with that specific name for its polishing transformation. And then there's a second polishing transformation because you may want to modify this GMF gen model, which is really horrible. So this holds all the information the GMF generator needs. It has properties there which hold Java code. So let's go to the properties. You can change a lot of aspects of the code generation from here, whether the editor supports live validation and so on and so forth. This information only lives in the GMF gen model. So there we could have another transformation called fix gmfgen.eol, and Eugenia will pick this up after GMF has generated the default GMF gen model, and it can apply changes to that as well. It's these two polishing transformations that you can have in a Eugenia project. This is, for example, how the transformation we would use if we wanted our diagram project to refer to another project that, for example, holds custom Java figures for our graphical syntax. We would need to add that other project to the dependencies of this project, and this is controlled by the GMF gen model. Anything else? Any other questions? No? Okay. We do have a little bit of time, so I think I'll just give you a quick demo of another way to create instances of your models that doesn't have to do with GMF. And to do that. Right, so we have here a model which contains steps, which contains, okay. So what I'm going to do is I'm going to go to step, and I'm going to have an attribute ID and I'm going to create my meta model. Right, so far we've seen 3 ways to create instances of your meta models: the reflective tree editor, the generated tree editor, and the generated GMF editor. What I'm going to show you now is a reflective textual syntax, XML-based textual syntax. So I'm going to create a new file, and I'm going to give it a flexmi suffix. So I'll call this evilbank.flexmi. Okay. So this is a reflective syntax, which means that I need to register my meta model in this workspace. Okay. So this is actually getting now parsed into an instance of my meta model. So I could have a right. You can see how this is turned into a speak action. This is turned into a decision. I could also give them IDs. Then I could create a transition from welcome to. Okay, you can see that this becomes a transition between this decision and this speak action. This is a flexible syntax, which means that the parser will do its best to instantiate elements of the meta model it's been pointed at. So the full name of this is speak action. Even if we type speak, it will figure out that, because in the context of models, of a model, what are my options? It's either a speak action, a transition. You know, I only have 4 or 5 options. What does it match against? This is a normal EMF model. So you could right-click, generate XMI. So this is another way to create your models if you prefer typing rather than pointing and clicking. Okay, good. Any questions? This is actually work in progress. This is something I'm very interested in and I'm currently working on. And there's a lot more to that, because in this way we can define like functions in models, so we can define complex element templates that can be instantiated many times in a configurable way. The latest version also supports visualization. We get this. So here we have a, what is that? Oh, FlexMI comps, yeah, this one. So here we have a small language. Just close everything else. So here we have a small component connector language where we have components that have ports, and then we have connectors that connect ports together. It's very similar to what you would find in a, for example, in a Simulink. That's a very similar to kind of a Simulink type of model. And here we have a model that conforms to this meta model in FlexMI, where we have a component with 2 input ports and 1 output port and the number of connections. And we can use model to text transformation to actually automatically generate visualizations of this model. So this is our speed monitor. It has a speed limit calculator component inside, and we can move between representations, which are automatically generated, so we don't have to do any dragging and dropping. All the information lives in the model, and then using model to text transformation, we can produce these views dynamically. That's just a kind of quick insight into things that we are working on at the moment in York in terms of textual and graphical editing. Okay, any final questions? No? Okay, so that's it for today, well, at least for this morning, and see you all after lunch for our practical. Thank you.